Good morning. In this session, we are going to discuss about two-dimensional electron gas. Here, the given figure shows energy band diagram of uh, N-type gallium arsenide and aluminum gallium arsenide heterojunction. That is, we are making a heterojunction with different band gap semiconductor materials. So, that is the junction, and we are going to consider the energy band diagram of that heterojunction. The aluminum gallium arsenide, we can dope it from a moderate level to heavily doped n-type, whereas gallium arsenide can only be slightly doped or even intrinsic. That is, gallium arsenide can only be lightly doped, whereas aluminum gallium arsenide can be doped from a moderate level to very high level. As already mentioned in the earlier classes, in order to achieve a thermal equilibrium, the electrons from wide band gap material, that is aluminum gallium arsenide in this case, has to flow into the low band gap material gallium arsenide, thereby forming an accumulation layer of electrons in the potential well adjacent to the interface or junction. One basic quantum mechanical result that we have found in the earlier classes is that energy of an electron contained in a potential well is quantized. That we all know, energy of an electron or any charged particle that is contained in a potential well will be quantized. Now here the phrase two-dimensional electron gas actually refers to the condition in which electrons have quantized energy levels in one spatial direction. That is, that direction is perpendicular to interface, but it is free to move in the other two spatial directions. So its energy levels are quantized only in a one particular direction, that is in a direction perpendicular to the interface, whereas in the other two spatial directions it is free to move. That is the main concept of two-dimensional electron gas. Now the potential function near the interface is approximated by a triangular potential well. Here figure A, it shows the conduction band edges near the junction interface, whereas figure B shows the approximation of triangular potential well. So that Vx denotes the potential. It is EEZ, that is charge of electron into electric field along Z direction, where Z greater than 0, whereas potential is infinity for Z less than 0. So using these potential functions, we can solve Schrodinger wave equation. Now the quantized energy levels thus obtained are shown in figure B. Here for in this case we are not considering higher energy levels. The qualitative distribution of electrons in the potential well is shown in this figure that you will have to draw. Also this figures also you have to draw. Then a current parallel to the interface will always be a function of that electron concentration and that electron's mobility. So here we already said that gallium arsenide is slightly doped. So the two-dimensional electron gas is in a region of low doping. So impurity scattering will be negligible. But the electron mobility will be large than if electrons were in the same region as ionized donors. So electron mobility in this case will be large. The movement of electrons parallel to interface is influenced by Coulomb interaction of ionized impurities in the aluminum gallium arsenide. Now the net result of these forces can be reduced by using a graded aluminum gallium arsenide and gallium arsenide heterojunction. Graded means we are placing these layers one over the other. Okay, that is we are placing thin layers of aluminum gallium arsenide and gallium arsenide one over the other, that is more than two layers. Now such graded layer will be as such, that is aluminum gallium arsenide. This X actually denotes the ratio of composition of aluminum gallium etc. or mole fraction, and that X can vary with distance. In this case this graded layer of aluminum gallium arsenide is sandwiched, that is it is placed between N aluminum gallium arsenide and intrinsic gallium arsenide. Now figure shows the conduction band edges across that graded heterojunction, which is in thermal equilibrium, the electron in the potential well are separated from the impurities so that electron mobility can be increased even above the heterojunction formed. So this all that's all about the two-dimensional electron gas. That all these slides you can just mention, because if it is asked like a short question, you will have to mention all these slides. It's not very difficult to learn, right? So please go through it. Thank you.